by Joe Maciejko, Nematic order in fractional quantum Hall liquids. Let's take here.
Oh, yeah. Sure. Thank you. Okay, so first of all, I'd like to thank the organizers for inviting me to come to this very nice workshop. I've been learning a lot, and I'm looking forward to learning more. So today I'll be talking about something that we heard about already a little bit before in the context of experiments. Today I'll be talking about some theory on nematic order in fractional quantum Hall liquids. And the work that I will be presenting today was done in collaboration with a number of people. So Shivaji Sandhi, Steve Kivelson, and Nicolas Regnault, who did the numerical work, that will be part of the presentation today, and also some earlier collaborations with Ben Su and Yeji Park. And so, there is a recent preprint that will constitute sort of the second half of the talk, and then in the first part I'll review some earlier work, and essentially this more recent work can be seen as a follow-up of the previous work. So first off, what do I mean by a fractional quantum Hall nematic? So as Gabor mentioned, this can mean different things for different people, and so here I will take the fractional quantum Hall nematic to mean a proposed novel state of matter where I have a coexistence of topological order of the fractional quantum Hall type, coexistence of this order with conventional broken symmetry nematic order. So first off, if we think about intrinsic topological order, it's a global form of order, and so one might think that in general, and it's true that it's insensitive to symmetry considerations which are local in nature, and so therefore we could think that the two are sort of very much decoupled in a sense, and we can imagine many possible broken symmetries. From the previous talk by Philip Kim, we heard about some beautiful experiments where we can see coexistence of broken symmetries and quantum Hall order. And so in one sense, one might ask, why do I focus specifically on nematicity? So one first answer, of course, comes from experiments, and we know that phases where there is some sort of spatial order, or at the very least, even if we don't have a spontaneous breaking of spatial symmetries, at least there is a strong response to perturbations that break spatial symmetries, for instance, tilted fields. And those types of phases seem to be ubiquitous in the quantum Hall context, in the fractional quantum Hall context in particular. For instance, if I think about higher Landau levels that have filling, and also some more recent work on other filling fractions. So I won't review experiments exhaustively, but I'll just point out a few where one might perhaps see the coexistence of topological order and broken symmetries. Although I really don't want to make any definite statements about what type of phase one has in the experiment, but just take this as a motivation for the study we want to undertake. So here, this is taken from an experiment in the Jim Eisenstein's group in 2011. And so there they were looking at filling factor 7/3, and they applied an in-plane magnetic field and tried to see what happens in the presence of this in-plane field. And what they saw very strikingly was that even if we apply very large tilts, first of all, the Hall conductivity seems to be, the Hall resistance seems to be to remain quantized. But one develops a very large anisotropy in the longitudinal transport. And furthermore, there is a sort of interesting temperature dependence to these effects. So of course we know that an in-plane field will explicitly break the rotation symmetry. On the other hand, it might perhaps be hard to imagine that if the only effect is the breaking of the symmetry explicitly, then why should there be such a sort of non-monotonic temperature dependence? So another effect of the in-plane field is that it can affect the effect of two-body interactions in if we project things to the occupied Landau level, the partially filled Landau level. And so we might expect that as the in-plane field is applied, on top of breaking the symmetry, maybe one tunes a coupling constant in the underlying Hamiltonian. So one possible interpretation of this upturn here at some particular temperature would be that maybe one has some kind of isotropic to nematic transition, or some transition at which, on top of having an applied symmetry breaking field, maybe the system also would like to develop some spontaneous anisotropy. Okay. And then, of course, how do we explain this particular temperature dependence is really not an easy question. I'll have a few comments at the end regarding that. Then we heard about the beautiful experiments in Gabor's group at 5.5. And in this case, it's very striking because one sees a spontaneous anisotropy truly spontaneously in the absence of any, at least intentionally, a field that would break the spatial symmetries because they apply some hydrostatic pressure. On the other hand, it's not clear whether there is a Hall plateau or not in this anisotropic phase, so it's not quite clear whether it would be a phase where we have coexistence of topological order and broken symmetry or not. And finally, I'd like to point out a slightly older experiment in the Maciejko's group, also at 5.5, where they apply a tilted field in this case. And they see a large anisotropy in the presence of a tilted field. So there's no Hall plateau that's reported, but as the temperature goes to 0, the longitudinal resistances appear to vanish. So it would seem to indicate that at 0 temperature we have some sort of incompressible quantum Hall liquid, but at finite temperature there's some large anisotropy that perhaps would be hard to explain if the only effect of this tilted field was to break the symmetry. Okay, but again, here I'm just being tentative. So again, just to reinforce that, a bit of a disclaimer. So today I'll be talking about the concept of a fractional quantum Hall nematic phase. So it might be that these experiments may or may not be explained by this physics, in particular because in some cases it's hard to tell whether the nematic phase is topologically ordered or not. But nonetheless, I will focus on this phase as not only as possibly relevant to experiments, but also as a conceptually interesting novel phase of matter where we have the coexistence of two types of order. And as will become clear a bit later, there was also a theoretical motivation, which was some work that Haldane did on some geometrical perspective of the quantum Hall effect. And here, hopefully, I will try to link his ideas to the concept of nematicity in the quantum Hall effect. So the main questions I would like to ask in this talk is, first of all, is there a generic mechanism for a transition from an isotropic fractional quantum Hall liquid to a fractional quantum Hall nematic? And if so, what would be the effective field theory of that transition, assuming that the transition is continuous? And finally, is it possible to realize this transition, at least in a microscopic model of interacting electrons, which might give us some confidence that this type of physics and this type of transition could actually occur in a real material where we have electrons in a Landau level. And so the claim that I will make in this talk is that the isotropic fractional quantum Hall liquid is actually naturally proximate to a fractional quantum Hall nematic, in a sense sort of coming from really lowest Landau level physics, in a sense independently of the details of the material. And the main point upon which this is based is that and I'll argue that it might be true, is that the Gervin-McDonald-Platzman mode in the long wavelength limit corresponds to gap nematic fluctuations, which would condense in a quantum mechanical way at a putative isotropic nematic quantum critical point. So I will sort of unpack this statement as the talk goes along. So in our discussion, this GMP mode plays a central role. So let me remind you what this mode is. So this was discussed by these gentlemen back in the 80s, and this is essentially a neutral collective mode in the fractional quantum Hall effect, which you can think of as an intra-Landau level version of the inter-Landau level magnetoplasmon mode, or which in the long wavelength limit becomes the cone or cyclotron mode. So this, by contrast with the magnetoplasmon, this intra-Landau level mode only exists in the fractional quantum Hall effect, does not exist in the integer quantum Hall effect. And if you look at typical energy spectrum, such as obtained by exact diagonalization in the fractional quantum Hall effect, this is typically what the spectrum looks like. So there is a continuum at higher energies of states, which corresponds to multiple quasi-particle, quasi-Hall pairs. But at lower energies, there is a coherent excitation, a coherent collective mode, which has this interesting minimum, which is called the magnetoroton, which you could think of as the sort of quantum Hall analog of the roton mode in bosonic superfluids. And essentially, near this minimum here, this corresponds to a single quasi-particle quasi-hole pair. So you can think of this as, indeed, as a sort of particle-hole excitation of Laughlin quasi-particles. But what is interesting is that, and I'll sort of try to substantiate this statement in the next slide, is that if I look at not at this minimum here, which has finite momentum, but at the log wavelength limit of this mode, which is the higher energies, then the claim is that this mode actually has a quadrupolar symmetry. Okay, so how do we know this? So actually, the main evidence comes from numerical studies. So it was shown early on, and also in more recent work, that actually, if you perform an exact diagonalization study of the quantum Hall effect on the sphere, then you will see that this long wavelength part of this mode has angular momentum L equal 2 on the sphere. So you might say, well, actually, it's hard to separate this mode from the continuum of other states. That's true, but what these authors have done is actually to construct variational wave functions, trial wave functions for this collective mode, and they found that they found very good agreement with the numerical studies with exact diagonalization in this regime and also here. But using this approach, it can actually determine the quantum numbers of this mode as the momentum goes to 0. And again, they found that this mode has angular momentum L equal 2. So this was found to be the case both for the Laughlin state and also for at least one non-abelian state, the Moore-Reed state. So this state also has a fermionic neutral mode, but here I'll be focused on this bosonic mode, which has L equal 2 in both cases. There's also some more heuristic arguments that argue that this would be the case. So in the composite boson theory, which by now is recognized as more of a heuristic way of understanding the quantum Hall effect, but nonetheless, in this approach, one can show that only the quadrupole part of many quasi-particle configurations, many vortex configurations in this description, contributes to the log wavelength structure factor, which implies that this structure factor goes like q to the 4th in the long wavelength limit, which is known to be true from other methods. And to understand how this connects to this GMP mode, recall that in GMP single mode approximation, so this is how they originally studied this mode, then the structure factor is saturated by this collective mode. So really, this q to the 4th contribution comes essentially from this GMP mode at long wavelengths. Okay, so there's some good evidence that this mode carries angular momentum 2 at long wavelengths. So building on this, so Haldane and co-workers developed some sort of geometrical theory of the fractional quantum Hall effect, where they argue that the right way of understanding the long wavelength limit of this mode is as some kind of fluctuating intrinsic metric, which is a real symmetric matrix, which is fluctuating because this is a collective mode, and so in general it would have some spatial and time dependence. And so this is not too hard to understand, at least from the point of view of degrees of freedom. So the idea is that, okay, so first of all, they require this metric to be unimodular, meaning that the determinant of this matrix is equal to 1. And it's not too hard to understand that this is an object that describes quadrupolar fluctuations, because if you take a symmetric rank 2 matrix and you form this, you write down this equation where, let's say, x1 and x2 are coordinates in the plane, then you will see that the equation where GAB xa xb equals a constant describes an ellipse. And if you vary g while maintaining this constraint of unimodularity, then you will see that essentially you're just parametrizing a set of ellipses of fixed area, so essentially quadrupolar deformations of the circle. Okay, so it's just a way of packaging or writing down a quadrupolar object. Okay, so for just one slide for the experts. So besides interpreting this GMP mode as some kind of fluctuating metric, they also went on to construct anisotropic versions of the Laughlin state. And in other words, now we're describing the ground state. And so the the standard rotationally invariant Laughlin state in this description corresponds to having a metric that is essentially the identity matrix. So essentially we consider the rotationally invariant case, but they went on to generalize this and to construct anisotropic versions of the Laughlin state that have essentially a fixed quadrupolar deformation that they then use to be trial ground states for an anisotropic, explicitly anisotropic Hamiltonian. So let me just explain briefly how this wave function is constructed, because I think it's interesting. So if you remember the fact that the lowest Landau level, the Hilbert space in the lowest Landau level can be mapped to the space of analytic functions or holomorphic functions, then one can actually write down the operators, the ladder operators that move you within the Landau level as essentially multiplication by the complex coordinate z or a derivative with respect to z. Then the regular Laughlin state can be written in terms of ladder operators in this form, where we are creating essentially states for particles I and j. We're moving up the ladder within the Landau level. And in this language, rotation symmetry corresponds to the conservation of the number of A bosons in the lowest Landau level. And so the way to construct, at least one way of constructing an anisotropic Laughlin state that nevertheless remains in the lowest Landau level is via this quadrupolar deformation. So it turns out that you can take this quadrupolar deformation and out of it construct a Bogoliubov transformation of these operators that essentially mixes A and A dagger. And then you use these transform operators as your new ladder operators, and you construct your Laughlin state out of those. But now, because these transform operators have mixed A and A dagger, now this state will be a linear superposition of states with different number of A particles. And therefore, this state has indefinite A particle number. And therefore, because of this statement here, breaks the rotation symmetry. So it's not rotationally invariant. And now if you take this state and you compute, for example, the electron density of a droplet, then you will see that, okay, you can tune from a circular droplet to some anisotropic droplet. Okay. So this was their interpretation. So now what we want to say is that maybe a simpler way or an equivalent way of understanding this is that this unimodular metric is equivalent to a nematic order parameter. Okay, so conceptually, it's not too hard to see, because if you have quadrupolar deformations, we know that this is what nematic order means. It's a headless vector. More mathematically, you can just see that if you take a unimodular symmetric matrix and you write it as the exponent, matrix exponential of some matrix, then you will see that this matrix Q here in the exponent has to be traceless. And since it was symmetric, because G is symmetric, then you have a traceless symmetric matrix, which is what a nematic order parameter is. Okay, so you can also package the two independent elements of this matrix into a single complex number that has an amplitude, which describes the amplitude of nematic order, and some phase here, which is essentially the phase of the angle of your nematic. And in here, this angle, if you rotate this nematic by pi, you get the same physical state, which is why this order parameter needs to remain constant. Okay, so if we now the idea is that we will try to use these ideas to argue that in general, at least if we tune some parameters, maybe we can engineer a transition from an isotropic fractional quantum Hall liquid to a nematic one. So deep in the isotropic fractional quantum Hall liquid, this long wavelength part of the GMP mode is kind of buried at high energies in this continuum. But you might think, or you might imagine, a situation in which upon acting with some external parameter, maybe you can bring down the energy of this mode, and if you can bring it down sufficiently low, then maybe you can imagine condensing it, and so essentially collapsing this gap. And if this gap collapses, then because this mode carries angular momentum L equal 2, then naturally you would essentially condense a boson with angular momentum 2, and then you would get a nematic phase where you are spontaneously breaking the rotation symmetry. So this essentially gives us a natural route to a continuous transition from an isotropic Laughlin liquid to a nematic one through the softening of this long wavelength part of the GMP mode. Okay, so near the quantum critical point, if we were able to engineer such a quantum critical point, then because the gaps are small here, sufficiently near the critical point, then we expect that the physics should be universal and that we could describe it by a long wavelength effective field theory. Okay, so what would this effective field theory look like? So if we try to construct it, so there will be a time-dependent part which corresponds to quantum dynamics, and then there is a Hamiltonian. So the Hamiltonian, the time-independent part, we expect that we can just write it down by looking at the symmetry. So it will be fixed by the continuous SO2 rotation symmetry. So it's essentially, it's a sort of phi-4 type theory, but we need to account for the fact that this is a spatial symmetry. Okay, so there will be some sort of stiffness term, and then a term that a mass term that tunes the transition, and then in 2 + 1 dimensions we would stop here generically with some quartic interactions. Okay, so now if we look at the time dependent parts, naturally you might think that, okay, maybe I would write down some sort of relativistic dtq squared term, but actually because there's a large magnetic field, this is a quantum Hall state, time reversal symmetry is broken, and so there is a term that is lower order in time derivatives that is allowed, so namely a term that is first order in time derivatives, and that has this form, and this is basically a Berry phase term, and it makes the critical dynamic critical exponent at the transition to be z = 2. And I would like to point out that, okay, so one can sort of write down or conjecture an effective field theory of this form from general principles, but I would like to point out that actually we can realize this scenario can be realized explicitly in the composite fermion theory within the mean field theory approach, a scenario in which precisely what I talked about happens. So there is a transition from an isotropic to a nematic fractional quantum Hall state via the condensation of this GMP mode, which can be seen explicitly within this approach, and the resulting effective theory indeed has this form. Okay, so this was done by Fratkin and collaborators. So if I think about the possible phases in here, so it turns out actually that if you go back to this mapping between the matrix representation of the nematic order parameter and this complex number, then this theory is essentially has the same form, in fact, to lowest order as the theory of a complex scalar. There are some anisotropic terms, but they are irrelevant at the transition. They will affect the nematic phase, but at the transition, they are not relevant. And so essentially, what we have is a Mexican hat potential if we tune this coupling constant to be negative, where essentially the two axes in the plane correspond to the two independent nematic orientations. And so there is essentially an SO2 or a U1 manifold of broken symmetry states that we can access. Okay. And so the phase diagram that would come out of this would be pretty standard. So essentially at zero temperature, there would be a direct continuous quantum phase transition from an isotropic Laughlin liquid to a nematic Laughlin liquid. And the quantum critical point, because we have z = 2, would be in the 2D dilute Bose gas in Versailles class. So it's essentially Gaussian with some logarithmic corrections. And emanating from this would be some finite temperature transition at which disclinations in the nematic unbind. And if we look at this, the nematic side of the transition, so in the nematic phase, because the collective mode that condenses is neutral, we would expect that the DC Hall conductance remains quantized. But nonetheless, we have a gapless Goldstone mode, which is the nematic mode, which is neutral, once again, that does have an anisotropic dispersion in general, reflecting the broken spatial symmetry. And interestingly, the disclinations actually carry some fractional charge and statistics. But don't worry about this. Actually, because these are sort of XY type defects, they have some logarithmic interaction, so the concept of statistics here may not be well defined. But nonetheless, they have some unquantized charge. Okay, so this is an effective field theory that one could conjecture, write down based on some general principles. Now, can we actually engineer this transition in a microscopic model and hopefully beyond sort of slave particle mean field theories? So what we did was to numerically study a model of interacting electrons in the lowest Landau level. And so here, because we're only interested, at least so far, mostly interested in the proof of concept, we studied the simplest case, which is filling factor 1/3, and we studied the theory on a torus. And the model we consider is essentially a model that only contains the first three Haldane pseudopotentials. So if you pull out, so there would be three coupling constants, V1, V3, and V5. But let's say V1, if we pull it out, we'll just set the energy scale. So actually one has two tuning parameters, V3 over V1 and V5 over V1. So if these two parameters are 0, then we have the V1 only model, which is known to be exactly solvable, and whose ground state is the celebrated Laughlin state. And if these parameters are not 0, then there's no exact ground state that at least I know of, and one needs to study the model numerically. So the first thing we did was to do the simplest thing we could think of, which is to do a variational calculation. So what we did was actually to consider the anisotropic Laughlin states I mentioned earlier as the variational states for spontaneous breaking of rotation symmetry. So I want to point out that previously these states were used as trial states for explicitly anisotropic Hamiltonians. Here I'm trying to explore the possibility that anisotropy develops spontaneously because the Hamiltonian is explicitly rotationally invariant. And so for that we need, first of all, a variational parameter. So it's this sort of metric or parameter space of quadrupolar deformations, which can be explicitly written in terms of the amplitude and phase of the order parameter. And what we do is to minimize this variational energy, which is explicitly independent of phi, because the Hamiltonian is rotationally symmetric, but which depends on the amplitude, and we can try to search for minima of this variational energy. So that's for the wave functions, but we also need a microscopic definition of the nematic order parameter that can be calculated from these wave functions. So here there's a bit of a subtlety. So because we are considering the torus geometry, the boundary conditions at finite size explicitly break the continuous SO2 rotation symmetry down to C4. So actually, this continuous degeneracy of nematic states is broken down to C4. So we only have two distinct nematic states on the torus. And so in fact, so the proper microscopic nematic order parameter to use in this calculation here would be an Ising nematic order parameter. So in principle, any microscopic definition that has the right symmetries would be a legitimate choice of nematic order parameter. So here we chose the simplest thing we could think of, which has the right symmetry. So it has essentially sort of d x squared minus y squared symmetry. Okay, so what we do is we minimize the variational energy, and then we calculate the nematic order parameter in the optimal state using this formula here, where psi is the optimal trial state. So this is the variational phase diagram. So we find that there is indeed an isotropic to nematic quantum phase transition at there's a nearly vertical phase boundary at roughly V3 over V1 equals 0.6, and as far as we can tell, the transition is continuous, at least within this variational approach. And so here, this is a plot. So the relationship between the variational parameter, the device field, if you want, and the order parameter itself is a bit nonlinear, but nonetheless, the order here is non-zero, and it's 0 here. So and because these variational states, these anisotropic Laughlin states have actually the same topological order as the regular Laughlin state, then this ordered phase here is truly fractional quantum Hall nematic. Okay, so this is a variational calculation. Would like to test this a bit further, and so we did exact diagonalization of the same model on the torus, so up to 13 electrons. Turns out that n equal 12 has some commensuration effects. We don't see the transition, and 12 seems to be quite different from the other cases, so it's not yet fully understood what happens here. So I'll be presenting mostly data for 10 to 13. So this is the data we obtain. There are 3 rows in here, so we compute the gap in the zero momentum sector. We also compute the overlap of the exact ground state, the numerical ground state with the Laughlin state, and finally we compute the overlap of the numerical ground state with the a state essentially that would lie completely the extreme right of this x-axis, which is the state in which essentially the pure V3, the ground state of the pure V3 Hamiltonian. So of course there's still some fairly strong finite size effects, but at least qualitatively we seem to be able to discern roughly 3 phases. And so on the left-hand side there seems to be essentially a phase in which the gap of the original Laughlin state remains finite and then closes at some gap closing phase boundary. So clearly that phase would be adiabatically connected to the Laughlin state. The overlap with the Laughlin state is quite large and then decreases as we go near the transition. And then there seems to be roughly 2 more phases. So there seems to be a phase here in the lower right corner of the phase diagram whose overlap with the pure V3 ground state grows as we go more to the right. And then finally there seems to be a third phase here that has 0 overlap with either of these ground states that is in the top right corner. So okay, so we conjecture that this phase here on the right-hand side, lower right of the phase diagram, is adiabatically connected to the pure V3 state because the overlap seems to grow as we go further to the right. And for this upper phase here, we have to discuss what it might be. So if I actually, okay, so the conjecture is that actually this phase here in the lower right corner is the stripe phase, and that the phase here in the upper corner is the nematic that we found in the variational study. So let me try to argue why this might be the case. So variationally, we know. So actually, if you compare this, the numerical gap closing phase boundary seems to be quite close to the variational study here, which might be an accident, but at least it's encouraging. And so according to the variational study, then these 2 phases here seem to have some breaking of spatial symmetry. So the variational study predicts that these 2 phases would be a nematic, but in exact diagonalization, there seems to be 2 different phases. So to try to tell which one is the nematic, then we would like to compute the order parameter itself in these phases, the nematic order parameter, to see if it's 0 in one phase and not in the other. Of course, we can't do that because there is no spontaneous breaking of symmetry in a finite size system. So the most we can do is to calculate a nematic susceptibility to see if it's large in one phase and not in the other. And to do that, we need to actually apply a symmetry breaking field to try to calculate the order parameter as a function of this small symmetry breaking field, and then take the slope or the derivative of this order parameter with respect to the symmetry breaking field to extract a susceptibility. Okay, so if we do that, so again, there's some fairly strong finite size effects. And it might seem that the physics disappear, although we would really like to go to higher system sizes to check things, but that's hard to do. And so what we have for now is that at least for some system sizes, there is some large nematic susceptibility in the upper right corner of the phase diagram. So this leads us to conjecture that this phase C here is the one that we saw in the variational study. So of course, in the variational study, we only have a nematic order parameter in there, and so we can't access the physics of this other phase that seems to lose to the nematic, rather that seems to win to the nematic in this part of the phase diagram. So what we did to try to ascertain the physics of this phase here is to study the pure V3 Hamiltonian. And so what we did was to study the dependence of the gap in this phase as a function of system size, and also as a function of this symmetry breaking field, which maybe I forgot to mention it, which is essentially what we do is we change the aspect ratio of the torus, and so we're explicitly breaking the C4 rotation symmetry of the torus, and that's our symmetry breaking field. Okay, so what we find is that first of all, the gap of the pure V3 model is strongly dependent on system size and also on the aspect ratio, by at least compared to the Laughlin state. So if you look at the gap of the Laughlin state as a function of system size, it truly is an incompressible phase. The gap remains finite as we increase the system size. Here in the pure V3 case, it seems that the gap varies a lot with system size, and at least within this range of system sizes suggests that maybe this phase is actually gapless. Now, to try to see if it's gapless, is it a broken symmetry state? Well, again, we compute the gap as a function of aspect ratio. So in the pure Laughlin case, what we find is that the gap is essentially independent of the aspect ratio, and that seems to correlate with the fact that it's an isotropic phase, whereas in the pure V3 case, the gap is highly dependent on the aspect ratio. So we take that to suggest that in the thermodynamic limit, this might be a phase that breaks the rotation, that breaks some spatial symmetry spontaneously. So because it's not a nematic, at least variationally, then we conjecture that it might be a phase that is naturally proximate to a nematic. And so the simplest, the most natural choice would be a stripe phase, which can melt into a nematic via a melting transition. So of course, I'd like to point out that there's an alternate possibility that was proposed before, which is that this is actually not a broken symmetry phase, but that this is a novel fractional quantum Hall state. And so this was work by Janendra and coworkers and also some earlier work, so I'd like to point that out. Okay, so I'm almost done here. So just a few words about experiments. So the main result of our work is that there seems to be a natural way for a fractional quantum Hall, isotropic fractional quantum Hall liquid to become nematic. Now, is this relevant to experiments? So far we don't really know, but I would just point out that there is a way of reconciling some of the data, at least the Eisenstein data from 2011, with the physics that I've described. So one might actually reconcile this data here. So this interesting dependence of the resistance at sort of below this putative nematic transition temperature by invoking the formation of domains. So if you imagine that you have a gallium arsenide sample, so actually you don't have a full SO2 rotation symmetry. You only have a C4 symmetry because the gallium arsenide the lattice structure as a C4 symmetry. In fact, it may even be not fully C4 symmetric, as Bert mentioned yesterday. But let's assume for now that it's C4 symmetric. Then you would expect that because this is a spatial symmetry, if you have a sample with edges, then the edges will naturally pin a preferred nematic orientation. So if you have a full C4 symmetry, this is what you would obtain. Now, if because the sample is not fully square, or because the lattice has some C4 symmetry breaking, then you might actually expect that in general one orientation will be preferred at the expense of the other. And what this means is that one of the domains will grow at the expense of the other. So in general, you might have 3 domains here in the simplest case. And then what you might expect is that if you have a domain wall, naturally you could expect that there is a low energy mode that could carry current. And in this scenario, if you actually look at the along this direction, you wouldn't have any current flow because these are gap phases. At least they have a charge gap, and so you would expect that the conductivity in the x direction is 0. But here, the conductivity in the y direction could carry could be finite due to these current carrying modes. And if you look at this, then the y resistivity would go to 0, and the x resistivity would go to a finite number. And this would increase as you go through the transition because this is where you have the formation of domains. Okay, so I would like to conclude. So there seems to be evidence from both theory and experiment, perhaps, that the isotropic fractional quantum Hall liquid is naturally proximate to a topologically ordered state that also exhibits nematic order. The mechanism for the transition, we argued, or for that particular transition, is the condensation of the long wavelength part of the GMP mode, which carries angular momentum L equal 2. The transition would have a Berry phase term, so it would be a Z equal 2 transition. And there seems to be evidence that this transition can be engineered in a microscopic model of interacting electrons in the lowest Lambda level, although we would like to do some further numerical studies to maybe try to test this further. And there might be experiments perhaps trying to see if this GMP mode indeed softens under the influence of some parameters that might help to corroborate this theory with experimental data. Thank you very much.
I wonder whether the following is the reason for your difficulty in getting the numerical answer of the nematicity. My understanding is that suppose you have more than one superpotential, suppose of V3 and V5, one of them favors C3 and one of them favors C5. And then now there could be a case where you did that I could get 2 states that are degenerate. Suppose I start with C3, but then the other one is a linear combination of C3 and C5. You get degenerate. I think that the issue can be solved in two-body problem. But however, since your system is rotational symmetric, so I think that in order to see the broken symmetry, one would have to, or to see the spontaneous broken symmetry, one have to add a very tiny symmetry breaking field to break it. And it's like exactly the situation of if I try to get a rotating a vortex lattice in a pure rotational system. If I solve the Landau problem, you cannot get the vortex lattice in the both cases. You have to add a very tiny rotation. So I think if you add a very tiny rotation, I think phase can separate out separately. I really think the whole thing can be settled in two part of the issue.
Mm-hmm. Yeah, I think.
Two part of that level.
Okay, thank you.
I can understand. So one thing is, so when you go with the spectrum, so you should expect the gap You were showing gaps in the view.
Yeah, right. So we did because these are costly computation. We did a limited study of the gaps at all momenta to try to see. So actually, it does seem that this transition here. Okay, again, it's there's some fine size effects and it's complicated, but there seems to be a lot of things happening. And a lot of modes are going down here, not only at zero momentum. So here we don't actually have a clear-cut collapse of the gap only at zero momentum. It seems like we have a lot of instabilities at sort of many different wave vectors. So it's actually quite. It's not clear at all whether is this okay. So I said stripe. Is this truly a unidirectional phase? So maybe I should have been a bit more careful. So we believe that there is some breaking of spatial symmetry here, but exactly what and presumably some sort of translational order because we see really soft modes at many wave vectors. But what exactly is the nature of this phase here? So the conjecture that the stripe phase is the simplest thing I can imagine, but there could be other things too.
Okay, just two more questions. How well do your numerical results correspond to Duncan's trial wave function with the metric?
Yeah, that's hard. So we try to think, can we compute the overlap? But that's hard because the numerics gives you a rotationally symmetric state because it's a finite-size system, but these anisotropic wave functions are broken symmetry states. So one would either have to construct a anisotropic state from the numerical data by taking a linear superposition, or do the converse, construct a symmetric state from a linear superposition of these anisotropic states. So we haven't done that actually.
If I understood the very end when you trying to explain the experimental data with the domain wall.
Mm-hmm.
So the assumption here is that the domain wall is conducting.
Right.
And why should it be conducting if it's a transition between two states that both have there's some kind of transition which is presumably kind of gradual. There's some domain wall between two states which are both quantized Hall states with nu equals a third, I think it is.
Right.
If there were modes, it's not clear that there'd be any edge modes at all. If there were, there'd be counter-propagating ones.
That's right. So there's certainly no topological reason. Yeah, there's no. I'm not saying that there's chiral edge states or there's no reason that there's no protection or anything that guarantees that we have edge modes. But I'm just saying that if you have of course, and the nature of the edge modes, if there are, will highly depend on the microscopic physics. But I'm just saying that there's a possibility that you might have modes that certainly would be counterpropagating. Again, there's no reason that there should be some chirality associated with them. But if there's just like if you have any localized potential, then there might be bound states. That's sort of the generic idea that you might have states in the gap that show up there.
But I'm just saying that if that's the case, I would expect that if you go to low temperatures, you freeze them out.
By disorder, you mean?
If there's any disorder or even just electron-electron interaction, it's just not. I could see that there'd be an anisotropy from this picture, but I would then think that if you went to low enough temperatures, both RXX and RYY
Right.
both go
Eventually.
to zero.
Right. That's right.
Maybe they wouldn't go to zero as fast.
That's true.
So then I don't know if there's maybe this thing.
That's right. And certainly in the experiments by Maciejko there, they do see that both resistances. We would certainly expect that in a truly fractional quantum Hall nematic at strictly zero temperature, then both resistances would go to zero. But maybe in some intermediate temperature range, then. So here it's more to say that the onset, as we go through the nematic transition, we have these domains. If these modes are created, then we would see that the resistance here goes up. But yes, this is hard to explain. Yeah.